Good morning. Hi, I'm Julian, and welcome to today's stream. As the title probably already told you, we are working on building a Kubernetes Cloud Controller Manager from scratch. Today is day 2 of this tutorial series, and let's quickly recap what we did last time. Sorry, my Stream Deck is still broken. I need to manually switch the scenes here. That doesn't look like the right screen. Let's try. Nope. What screen is this sharing? Screen, sorry. That shouldn't have been a problem. Nope, this is the wrong one. This is the wrong one, so it must be this one. Yes, perfect. I don't know what was wrong there. This is what we want. Sorry. I hope the rest of the stream is without any technical problems. Okay, so what even is a cloud controller manager? A cloud controller manager is part of the, or considered part of the Kubernetes control plane. And it's a bunch of controllers that connect your Kubernetes cluster with some cloud functionality. A controller is a loop of code that observes the state of some objects in Kubernetes and then tries to reconcile the real world with this. In our case, we also partially do it the other way around, where we observe the state of servers in real life and then sync back state from that to Kubernetes. Let's take a look at what controllers are part of the Cloud Controller Manager. First, we have the node controller. It tries to connect the node in Kubernetes with the server, VM, EC2 instance, whatever the name is in your Cloud API. The first step is that it tries to somehow match up the node object with the Cloud API object. It can do that by the IP address or by the host name or some other unique identifier. And then it will write that back to the node object into the spec.providerID field. Don't worry, we're going to take a look at all of these things in a moment. Next, it also annotates and labels the node with cloud-specific information. There is a list of well-known labels in Kubernetes. A very important page. And there you have stuff like the zone label, topology.kubernetes.io/zone, based on which zone or whatever equivalent that is in your Cloud API the node exists in. And you can use things like these to set up some geo-redundancy, some topology spread constraints, or similar. Then it is also responsible for figuring out all of the node's network addresses, like the host name, private and public IPs, and write them back. And also in case the node is shut down in the cloud provider, it reports that back to Kubernetes, so Kubernetes can quickly schedule the pods somewhere else. And also in case the node was deleted in the cloud provider, in the Cloud API, then it will also delete that node from the Kubernetes cluster. Because usually the nodes are responsible to register themselves with the API, but then when they are deleted, they don't unregister themselves. So the Cloud Controller Manager is responsible for making sure that the node objects are cleaned up at some point. Okay, then we have a root controller. We are actually not implementing this for this tutorial series because it's a bit more complicated to set up. And if your cloud has something like a private network where you can set up routing functionality, then you can take a part of the responsibility of your CNI, your container network interface, that is part of routing traffic to the individual pods on the nodes, and move that responsibility to your cloud provider, where the cloud controller manager then sets up routes in the private network for the nodes pod CIDR. So all traffic to pods on that node are automatically sent to that node, and the CNI doesn't need to make another kind of overlay network for that to function. And lastly, we got the service controller, which is responsible for setting up managed load balancers, or similar, for Kubernetes services with a type set to load balancer. Yeah, so these are usually what powers the ingress controller to then get the traffic and distribute it inside your cluster. Or if you have some special use case, you can also use this directly for a single service to just expose it to the world. But most people don't like to do that because load balancers in your cloud provider cost money. And if you have an ingress controller, you can save a bit of money. Yeah. Okay, so we last time we implemented the scaffolding for the cloud controller manager, as well as the node controller and the service controller. Except for some things in the service controller where I was just too lazy and the time was flying by, so I skipped them. And yeah, I wanna do this today, fix it up, and implement the missing cleanup logic that we skipped on last time. And also I want to set up a development environment using Terraform and Scaffold. We already started working on that last time, but we had some issues getting it to work. Okay, let's quickly check out the code that we wrote last time, and then we can start working. Okay, so everything starts with the main.go here in our directory. The code also is available on GitHub. I'm gonna post a link to this in the chat. If you want to check it out at your own pace, then you can. It should be this link. Let's test it. Yes, it's that link. So yeah, you can clone and check out the code there. Okay. Yeah, the main function is our entry point, and here we just copied a lot of stuff in the background. We are using the Kubernetes IO Cloud Provider library to implement most of the boilerplate, and this is part of the boilerplate. We just set up the CLI argument parsing logic, and then set up the command which parses the arguments, and then we run that command. Quite boring. There's some more boilerplate here to set up some controller user agents, I think is the purpose of this. Didn't really figure it out last time. And yeah, then we have this other function that we pass to our command above here, where we set up the cloud provider that is being passed to us. Our own code is actually registered through this, where we do a blanket import on the module CCM in our project here. And if we go into here, we have an init function which calls cloud provider.register cloud provider, passing in our provider name, which is hcloud from scratch, and the initializer for our cloud provider, new hcloud, new cloud. Yeah, and this just puts it into a map, and then if while it's starting, it reads the command line flag. So yeah, you usually pass in cloud provider hcloud from scratch, and it will read the cloud provider initializer under that name and start up that code, which is, I talked about this last time. This is more like a legacy thing, because previously all the cloud providers were integrated in the kubelet binary, and you could start it from there. But nowadays you just have the you just have separate binaries, but you still need to invoke it like this because there are still a few left in the kubelet that need this logic. Okay. Once this is started, we initialize our hcloud Go client with a token and a user agent and optionally a debug writer so we can see what actually happens with the API. And then we just create our struct cloud provider using the client. The cloud provider implements an interface called the cloud.interface here in the cloud provider library. And this is just a wrapper around returning multiple other interfaces, basically. So here on the interface, you have an option load balancer, and that itself returns an interface of type load balancer, where the actual functionality for the load balancer is implemented. So if we go into our cloud provider here, we see that we have a load balancer function, and that just returns another struct of type load balancer, which then implements the load balancer interface. Okay, we also have a number of interfaces that we just don't implement, like instances, because we do instances v2, which is smarter, better, easier, simpler, more optimized for our use case. This is more like legacy and you shouldn't use it for new stuff. Also, yeah, we don't implement zones, clusters, or roots. Roots we talked about earlier. Zones, I don't quite know what it does. It's an abstract pluggable interface for zone enumeration. Okay. And then you have the clusters, which is a way to get a list of clusters in your cloud, in your cloud project. I don't know. The documentation isn't really well done here, in my opinion. Okay. Let's check out the instances v2 interface first. It has three methods: instance exists, instance shutdown, and instance metadata. And the functionality is quite simple. Instance exists checks whether the server with that name exists, returns false if not, returns true if it does. Instance shutdown checks if the server is shut down, so Kubernetes can do whatever it needs to do with that info, and instance metadata returns a bunch of values that are then written back to the node object. So we have the provider ID, we have the instance type, the node addresses, the zone, and the region. And I don't have a good example here for my own code, but we have an example of this in the hcloud Cloud Controller Manager. Oh yes, one more thing. I work for Hetzner Cloud, so I will be using the Hetzner Cloud API today to demonstrate this, but basically all I'm doing also applies to any other cloud API you have. So yeah, there shouldn't be anything too specific about Hetzner Cloud here. Okay, so we can see here is a node object just with the values that we are writing back, or mostly with the values we are writing back. You can see that we have the instance type label set, we have the region label and the zone label set for topology-aware scheduling. We set the provider ID so we can later more easily identify the server in our API. And we return a number of addresses, for example, the external IP, the host name, and the internal IP, if it's available. Okay. Yeah, the only thing that's a little bit tricky here is how do we identify the server? So we have a function getServer for node, which checks if the provider ID is set. Then we just use that to get the server by its ID. And otherwise we try to use the node name to get the server by name. Because in Hetzner Cloud, by default, the host name of your VM is the same as the name of the server in our API. And by default in Kubernetes, the host name of your VM is the name of the node in Kubernetes. And with these two with these two conditions given, we can automatically assign the node to a VM in Hetzner Cloud API. Might not always be the case. In that case, you would need to use some other identifier or perhaps rely on the user putting in the provider ID for you. They can also patch that, and then you wouldn't need to use these heuristics to associate the node with the server. Yes, I'm using node for the Kubernetes node and server for the Cloud API server, just because it's the Hetzner Cloud terminology, but again, applies to any other cloud too. Okay, that's about the instances. Yes, the question is, hello, Domescope. Yes, it's a Golang day today here, as it is always in the Kubernetes world. Especially, and I was just gonna explain this because we use the Kubernetes Cloud Provider library. I mean, you could also easily do this with k8s, so the Rust client, or probably also the other clients. But we have the Cloud Provider library, and what it does is that it actually wraps the interaction with Kubernetes. So we only have the simple interface that we need to implement. And then if we check out where this is being called, nope, can we get the find usages? Yeah, so the Cloud Provider library has a node controller. Oh, also, I hope this text is large enough. If it's not, please complain, so I can make it a little bit bigger. The Cloud Provider library has a node controller, and there it calls the instance metadata method, and then that is used in the sync node function, which actually talks to the Kubernetes API. So we only need to implement this instance metadata interface, and then the library handles talking to Kubernetes for us. I mean, it's not complicated what they're doing, but any code that we don't have to maintain is good code. Except if there is a bug and you need to go in there and fix it, and then you need to get it upstreamed, and then it starts to become fun. Okay, next we have the load balancer interface here, and it's a little bit complicated. I think it would need a v2 iteration, in my opinion. So we have the get load balancer function, which just based on the service name and the cluster name, it gets the load balancer by name and returns that as well as a status. Get load balancer name returns a name, and sure load balancer is responsible for creating a load balancer if none exists, and making sure that the actual node ports in Kubernetes are reachable at the expected ports in the load balancer. So what we are doing is that we, using the Hetzner Cloud API, we check that we have services configured. Services are what endpoints are made available by the load balancer, and to which what ports are opened by the load balancer and to which ports in the backends they redirect. So we have the listen port, and we have the destination port, which is the node port. And because it's a simple setup here, we only do TCP and don't care about UDP or any other protocol. And also we update the load balancer targets, and the targets are the servers that are actually targeted by this load balancer. So there you would want all your Kubernetes nodes to be in there. Yeah, and then they will automatically receive traffic from the load balancer if they would pass the health check. But we also, just to keep it simple, we don't configure any health checks here. So they would always receive the traffic. Okay. Yeah, we also have update load balancer, which is very similar to ensure load balancer, but it only takes care of the targets. And then we have ensure load balancer deleted, which takes care of deleting load balancers. And then removing the, what is the name? If you block a deletion of a finalizer, yeah, it removes the finalizer, or rather the K-Cloud provider code removes the finalizer if possible, or rather if the load balancer was ensured to be deleted. Okay. Yeah, that's it with the recap. Oh, no. We did a lot of stuff last time. We also wrote some templates just to deploy it into our cluster. So here we just have a simple deployment, and it uses a service account. It has some tolerations, so we can actually start on any node, and then we pass in the arguments and the token, and then we have the a service account and binding us to the cluster admin role, just so we have all the access that we want. Bundled up in a Helm chart, and then we have a scaffold file which builds the image using Co and then deploys the manifests using Helm. Okay, let's get started. I would like to start by setting up a development environment using Terraform. So no Go code for the moment. Let's set up a Terraform project here. I haven't set up a Terraform project in a long time. Let's see how well this goes. Let's define a variable hcloud token. This is of type string. Then we have a variable count, which is of type number, and the default is 1, just so we can add and remove nodes in our cluster. Node count. Okay. Now let's think about what we did last time to create our dev environment and try to replicate it here. Okay, so we kind of need to create an SSH key and create it in the cloud, and then we create a server or multiple servers. And then, as far as I remember, we used k3s up, ketchup, I don't know how it's pronounced, to actually set up the Kubernetes cluster on there. Okay, let's start by checking the Terraform registry. For some SSH key. Is there some way to generate an SSH key? That's what I want to do. TLS private key. Okay. I hope this is still readable for you. SSH, no, TLS private key. Let's check out what arguments we have. Okay. So we specify the algorithm, and then we have a private key PEM, private key OpenSSH, and a public key OpenSSH and public key PEM. Okay. Perfect. So we can use that to use a resource hcloud. Let's get the Hetzner Cloud Provider up in here, and there we have a resource called SSH key. And we need to specify the public key, which would be the TLS private key .ssh public key OpenSSH. Maybe PEM would also work. We're gonna see once we try to use it to create a server. Okay. Next we can create a server. Resource hcloud server. Let's call that CP for the control plane. Why is it complaining? Okay. Name is CCM from scratch CP control. The server type is CPX1, which is the smallest ARM with a shared vCPU. Then we need a location where we want to create that. Let's do that in Falkenstein. We need to specify an image, the OS image that will be used. Let's use Ubuntu 2204. Oh yeah, we need to specify an SSH key. We're just going to use hcloud SSH key default.id. Do we need anything else right now? Oh, let's check out how we created the server. Type name SSH key location. Okay, nope, that should be it. And we're going to do the node count a bit later. Next, we also have the null resource, which we're going to use to run the k8s up. Or actually, we could use a provisioner in here. Let's use the remote exec provisioner. And oh no, this is because we want to run k8s up locally. We don't want the remote exec, we want the local exec. And then let's specify some commands here. And that would be k8s up. Okay, that sounds good. Can we do multi-line strings here? Yes, we can do here doc. Okay. So let's just do and then we can split this up into multiple lines. So it's a bit more readable. This is gonna be annoying. Well, we still got one extra long line here with the k8s extra args. Not sure if we can split this up more, or if that's just the way it is. Okay, the external IP, we can actually, oh, how does it work for provisioners? As you can see, I haven't done in-depth Terraform work in a longer time. No, this is Packer. We don't want Packer. Terraform provisioner. Yes. Okay, so there's the connection, which we don't need because we're doing a local exec, but we somehow need to make the private key available for k8s up. Do we have access to the variables? Okay, so what I'm trying to look is if we have access to the IP of the server in this provisioner code. Because then we can yes, okay, so we have self dot something. So let's do self dot might be this. Let's check out the server documentation again. Sorry, I'm doing this live. I haven't previously checked out how exactly I want to do this. Okay, so we get the public net back. Oh, we also have the IPv4 address just here. Okay, nice. And we also pass that to the arguments here. Nice. Yeah, let's execute this. I know it's gonna fail, but let's execute it and see how far we get. Let's run Terraform init. Okay, could not retrieve the list of available versions for provider HashiCorp HClub. Nope, there isn't one. So let's learn how we can define this. We need to make a, well, our docs kind of suck to get started. Always good to be the user of something to figure out. We need a required providers block in Terraform, right? Nowadays, yes, Terraform required providers. hcloud, its source is hetznercloud/hcloud, and the version is whatever the current version is. 1.42.1. Okay, then we need a provider block to initialize this. We're just going to use the hcloud token variable. So let's see. We probably also need to add TLS in here, which has a source of HashiCorp TLS, and the version is, we don't need it as you just saw, but I still like to have it in here. 404. Okay, that works. Now to actually do something, we need to populate this variable hcloud token, and we are going to do that using a variable file. So variable file, maybe variables, workspace variables, tfconfig, workspace variables. Yes, this sounds like the right page. Okay, so we already have a variable defined. The question is, can we read that, or how to read that from a file? Okay, let's just check out the documentation of Terraform apply. There should be a option. Oh, it's probably on Terraform plan. They share part of the flags. So some are only documented in the Terraform plan help output. Okay, so we have a var file argument. Load variable values from the given file. In addition, use the default files terraform.tfrs and auto.tfrs. Use this option more than once to include more than one variable file. Okay, let's create a new file then called credentials.auto.tfrs. And we'll put in an hcloud token. Okay, it's just some key value, so we can put a string in here. Let's make a copy of that and call that template. Yes, it's a text file, thank you. And then we're gonna add the actual credentials file to our git ignore to make sure that we don't commit it. So that's credentials.auto.tfrs. Nice. Git status. Let's remove it from the staging area. Credentials, yes, git status, and now it's removed. Nice. Let's remove the other stuff. Oh, also we got a Terraform directory. We don't want to keep that in our git state. So let's, because the directory only has like some backups for the provider binaries and other stuff, and we don't want to commit those. We can always download them from the registry. Okay, I'm gonna quickly hide the screen from you so I can put in the token, and then we can continue working. Okay. Nice. Let's get you back. Okay. One more thing I'm gonna do is I'm gonna mark this variable as sensitive, just to make sure that Terraform doesn't log it in any way. Okay, let's run Terraform plan to see what it would do. Okay, the argument command is required, but no definition was found. I did the local exec wrong. Let's check out the docs for local exec then. Local exec only accepts a command and not a list of inline commands. Okay, that should be it then. Let's try again. Oh, now my face is probably in front of this. Let's see, it tries to create a server, hcloud server. It will set up the SSH key in the cloud, and it will set up the SSH key. All of that sounds good. Let's run this. Nope. Let's run the plan that we just created. And I would expect it to fail on the provisioner because we don't provide the SSH key to it in a way that it could read the SSH key. Okay, it actually failed with just because it couldn't connect to the AP because the server isn't up yet. So let's put another block in here because for remote exec, Terraform actually does some retries. So let's put a connection in here. Host should be self.public self.ipv4 address, user is root, key type SSH. Let's check out the docs for this. Local exec, remote exec. Okay, so you have, it's a connection block to the top. Okay, outside of the remote exec block. Connection type SSH, and then we need the connection. We kind of need to specify the SSH key, that it should use the private key. Okay. So private key equals TLS private key dot SSH dot the open SSH. Okay, and then the remote exec should just wait. Actually, we could use cloud init wait. Cloud init is used to initialize the server, and sometimes it's still running while you can already SSH in. So by specifying that we want to wait for it, we make sure that the node is fully initialized before continuing. Right, so we had the inline argument here. Inline. Okay. Let's try that again. It should still fail. Okay, so because this failed, it marked our resource as tainted, and Terraform tries to replace it. Let's do that. Get some drinks going in here. Now it's waiting to be able to connect to the server. It tries, still tries. That's the benefit of the remote exec, that it just retries connecting until it's possible. Connected, it got the output, status is done, and then it tries to run the local exec, and it complained that the attempted methods did not work because we didn't expose the SSH key. So let's do that first. k8s up, install, help. Okay, so we have the SSH key, which is a path to the SSH key. Nice. So to make that work, we need to write the SSH key to a local file. Luckily, there is a provisioner for this. Okay, this is wrong. File provisioner copies files or directories from the machine running Terraform to the newly created resource. That's not what we want to do. What we want to do is just write a file. Maybe there is a provider for that. Let's see. Okay, so there's the local provider, and it has a resource local file and local sensitive file. I guess this is what we want, because the file is kind of sensitive. SSH, the content is equivalent to TLS private key dot SSH dot private key open SSH, and the path is gonna be I don't know, some kind of file, and we would also want to add that to our git ignore. And then we can use the same module, the same path in here, in the k8s up, to say SSH key is equal to this. And we kind of need to make sure that this writing happens before the local exec is called. So we are gonna add a dependency depends on to local sensitive file.ssh. This will make sure that this module is always finished before this is executed. Actually, we could possibly also make this we could just use the file name from the resource and just say that we want that ssh.file name. And then the dependency is automatically set up because we use its output. And to have its output, it needs to be executed before. Also, we don't hard code the path in two locations. Okay, let's try this again. Terraform apply. Okay, no version is selected. What is the version of this? 240. So let's put it into our provider list here. Local 240. Let's run Terraform init and run apply. And it should show that it tries to create a file and the server will be replaced. Let's do that. Still waiting for SSH ability. SSH is there and it's successfully running k8s up. Nice. Okay, so we still got an error. We need to figure that one out, but that's way better than what we got before. Let's connect to that server. SSH root at the IP. And we're going to use the identity file that we just created. And let's see why it failed. Failed to start. Yeah, okay. Thank you very much for not being helpful. Let's use journal cuttle to get some more info. I hope the flags are right. Yes. What? K8s fatal, K8s server cannot run executable found relative to current directory. Let's check out if Google knows anything about this. NixOS. This isn't NixOS. Okay, our flags might be wrong. No, but it is disable. Oh, we have node external IP. Okay. That was probably it. Let's try again. It will recreate the server. That's one of the downsides of using this construct. If we would have used a null resource, we could have just tainted the null resource and then the server could be kept. This way we get a new server and all the initialization time anytime we make any changes to the config. And that worked. Nice. Let's export the kubeconfig and then try to get the list of nodes. Nice. That worked. I want to do one more thing, and that is set up the worker nodes, just so we can test that we remove and add nodes and everything works as expected. Always helpful with the CCM because it does a lot of things around adding nodes and deleting nodes from the cluster. So if you want to test things around that, it's always helpful to have that set up. We are using a count here that is equal to var node count. And then we are just going to use, what is the variable name? Is it I really should use more Terraform more regularly. Count. Yes, the count meta argument. Thank you. Okay, so it's count.index. So I don't know why it doesn't show up. Oh yes, there's count. Well, thank you very much, Goland. That could have been quicker. Okay, so we just pass in the index, and then we basically use the same configuration, but in the local exec, we aren't doing a k3s up install. Instead, we are doing a k3s up join. Let's see what we need to specify here. Joining a cluster as an agent. Agent user, what? What is the user doing? Okay, let's just see what we are doing with the Cloud Controller Manager. Because we got lots of this stuff already set up here, just in a slightly different way. Dev up. Here we have the k3s join, server IP, channel. Okay. So we want to join. We still want to connect to the IP. We still use the same channel. We got some other extra arcs that we're going to check out later. And we also don't have a local path here. Do we have anything else? Yes, we have the server IP. Which k3s up automatically uses to get the join token for k3s and then join the node. So the server IP is equivalent to hcloudserver.cp.ipv4 address. That also sets up a dependency. Once the control plane is up and running, we are joining new servers to it. And then the flags that it doesn't use are disable cloud controller and cluster CIDR. Okay, nice. Let's do it. And yeah, let's start with one node. Terraform apply, it should show us one new server. It does. One new worker will be created with the name 0. Let's do it. And then I think one more thing that I forgot earlier. Oh, there was an error, unknown flag print config. Okay, let's just remove it. And recreate the server. One thing that I forgot last time was that we ran Cilium install helm. Yes, we ran helm install cilium against the repo. We could do that here, or we could use... Let's check out the Kubernetes provider here. Maybe there is some cool stuff here. Manage install charts in your Kubernetes cluster. Okay, nice. Back when I was still working on this, it definitely didn't have that many Kubernetes options. Okay, so we need to specify the path to the file. Okay, let's do that. Okay, so this is HashiCorp Helm. Helm source equals HashiCorp Helm. Version equals 2.11.0. Then we need to configure the provider, and the path is the module path dot kubeconfig. Yes. And then let's see, we can set up a Helm release. Let's check out Helm release. Name, repository, chart version, and some values. Okay. So the name equals Cilium. The chart equals Cilium. The repository is helm.cilium.io. The namespace is kube system, and the version is 1.13.1. Nice. Okay, we kind of need to wait for this control plane to become available, because only then we are writing the kubeconfig file. But there's no easy way to use some value here. So let's just put a specific depends on in here. So that would be hcloud server cp. Yeah. Let's see whether it successfully started the agent. It did not, it failed. Let's check out why it failed. hcloud server ssh. This one should be k8s agent.service. Flag provided but not defined, disabled. Disable. Okay, so perhaps we can also get rid of that flag then. There's no disable flag. Yeah, okay. Is there a node external IP? Yes, there is. Okay, that looks better then. Let's apply let's init and then apply Terraform apply. And it should try to install Cilium as well as replace the worker node. Yes, please. And now if we do an export kubeconfig, kubectl get ports, we should already start to see the Helm chart here. At some point, at least. Not sure how the provider works. And if it's where it is caching the registry and other fun problems. Oh, yeah, the path is wrong. It's kubeconfig.yaml. Let's move that to a local variable. Locals kubeconfig path is equal to this. Because yeah, it's another case of we had it defined in 2 locations. So let's reduce that to one local kubeconfig path. And also use it here. Okay. Oh, it doesn't have a dot. This should be the file name. Okay, sorry, I got distracted for a moment there. Yeah, nice. So the chart was successfully installed. And if we get all the pods, we see that Cilium is running, and also we see that we have multiple nodes which are available. Perfect. Nice, nice. Okay. Nice. That's it for our development environment. Let's put them into a git ignore. Let's put some more files into a git ignore file. We don't want to commit the state. Terraform.tf state. Backup. We do want the log file. We want the update to the git ignore. We do want our code for this. Let's put a new line at the end here. Is there some way to format this file? Yes. Oh, thank you. Okay, that's it. Oh yeah, get that Terraform log. And let's make a commit. Dev and using Terraform. Actually, I like this very much, and it's also So for our Heads on Cloud official integrations, the Kubernetes ones, we have these DevOps scripts, and they work, but they are like very hard to reason what they do. Also, I don't really know how I should extract these to be reusable between them, because right now they are like duplicated between the two repositories, and using a Terraform module might be the easiest way to get this done. So maybe it even found some nice alternative for work here. Okay, now that we have the code set up here, let's do one more. We need an output kubeconfig, and that is a value equals export kubeconfig equals, and then we use the local.kubeconfig path. And then if we run that Terraform apply, we can easily copy and paste this stream and have a setup development environment. Okay. Nice. Let's push. And then take a look at Scaffold, because last time we tried using Scaffold, it kind of didn't work well. Let's start by just building our image here, and then just get through the steps one by one. Oh yeah, I need to run export scaffold. What was the name here? Scaffold docs. Okay, so I tried to push every k8s CCM from scratch. Kind of doesn't have the permissions to push. What version of Scaffold are we using? Just because there is a hint that there is a new version. No, we are 2.6.3. That happened a long time ago. Why doesn't it have permission to push there? Okay, so docker login worked. Okay, maybe to quickly review what we are doing next. Okay, now the push worked. We will use Scaffold, which is a Kubernetes development tooling from Google, I think, an open source project from Google, where you write a Scaffold YAML file, and in there you can define a list of builds and how they are supposed to be deployed, and also a lot of other things, like a lot of options. And then it will automatically build your image, update the image variable in your manifests, and deploy that. And in addition to that, it also has some options to debug. So it automatically sets up the port forwards and the debugger. If it knows what kind of runtime you use, it can set up port forwards for you. Lots of cool stuff that makes it easy to develop the integration. So we were able to build the image. So let's try to run our stuff. So in this case, it deploys and then waits for the deployment to stabilize. Okay, so it complains that it can't schedule the pod because they have an untolerated taint. Uninitialized true. Let's see, I thought we had put in a toleration for this. node.cloudprovider.kubernetes.io. Okay, yeah, I think we forgot to put in a value here. Let's just use exists and not care for the value, and then it should work. Yeah, okay. So as you can see, we got a pod now that is actually assigned to a node, but we got a create container config error. And I guess that happens because the secret that we are trying to use here isn't defined. So let's get back to our dev env here, and we also need to create the secret from the hcloud token that we have. For that, we can't use the Helm release, but we can use a Kubernetes. Let's check out the Kubernetes provider. Okay, so it kind of just implements the basic APIs. I would love to know if they also, just because I'm curious, I would love to know if they also support custom resources. Custom resources. Doesn't seem like it. Ah, okay, so there's just a manifest resource where you can define custom stuff. Okay. Well, we don't need that. We just need the secret v1. So let's define this. Let's do it before the kubeconfig. hcloud token name is, what do we expect here? hcloud. Namespace is system. Data is token, which is equal to our variable hcloud token. And the type. What is the type for opaque stuff? Opaque. Okay, so probably the default if we don't put anything in here. Types are used if Kubernetes needs to know about the secret. Then you can specify a type and Kubernetes can automatically parse this. So there's a service account token and some Docker stuff. And then Kubernetes automatically knows how to read these types of secrets in case they're needed. So for example, the Docker config stuff is for image pull secrets. Okay. Okay, yeah. We still need to set up the depends on, because again, we need the control plane to be available. And also we need to configure the, the actual credentials here. Let's just hope that it works exactly the same as for the Helm provider. Kubernetes. No, it doesn't. Okay. Okay, so we just set config path like this. Okay, then we also need to add it to our list of providers, 2230. And that should be it. Let's run Terraform init. Terraform apply, and let's hope that it doesn't leak the token. Yep, no token leaked. Very nice. Yes, please apply. And the token was added. And we should soon see that it actually worked. Container creating, running. Nice. And now it's terminating all the others. Okay. Very nice. Very nice. And now that it's running, we should see the logs here. And there we see that it's currently in the leader election phase of its life cycle. So it tries to get a lease for this name. And once it has that, it will start actually processing events. And once that is done, we should see it. We should actually see the metric server and core DNS becoming available or running, because they are also, just like we were before, waiting on the taint to disappear, the uninitialized taint. Initializing node, very good. TCP lookup. What? Why don't we connect to the API? Now this is curious. There might be a misconfiguration in Cilium. We can't connect to the API. The Headstone Cloud API. Let's do a, what node is this running on? Worker 0, H Cloud Server SSH. Worker 0, yes, please. And then just do a curl api.headstone.com .cloud permanent redirect. Not found. Okay, so it can connect. So the question is, why can't the node connect to it? That sounds like a DNS issue. Oh yeah, that makes sense. That kind of makes sense because core DNS isn't running, right? So how would it resolve the DNS? How do we solve that in other cases? Did we do something different in the init phase here? We don't configure DNS in any way. Because I know that this script is working. This is, again, the upstream script from the hcloud Cloud Controller Manager. There I know that DNS is working, or rather that it can actually initialize the nodes. Well, well, well. I don't know what the issue is here. I mean, yeah, obviously it can't start, but why? Yeah, that's the that's the problem with these minimal images. You just don't have any environment to fall back onto. Okay, scaffold. I hope this isn't too boring for you. Cool. Okay, so we can overwrite the base image. So let's do that. Let's just say co from image Ubuntu 2204. Okay, previously we used scaffold run, which just deployed it once. Scaffold dev actually watches your directory and rebuilds and redeploys the image when it sees any changes. So it's more an interactive loop. And then there's also scaffold debug, yeah, which makes debugging possible. Okay, so that's set up. So let's go to exec again. Okay. Okay. So at least we get a bash, and then we can do ns lookup. No. Dig. Okay. Let's just update the package repository and then... Isn't there like ns lookup? Wasn't that a thing? Yeah. Oh yeah, it also can't connect to any other thing. Drill, dig, host, ns lookup. How do I do DNS lookups when I can't install anything? How many are there? Host, we tried host. Host wasn't available. Dig also isn't available. There's nothing. Nothing available here. Okay, let's try to amend the core DNS deployment to tolerate the DNS issue, the uninitialized tag, taint. Is that a deployment? Yes, core DNS. Okay, core DNS is running. Still doesn't work. Let's restart our pod. Waiting for the leader election again. Maybe we should just disable it. Leader elect equals false. Doesn't redeploy. The hot reload didn't work as I would have expected it to work. Okay, it still fails. Certificate signed by unknown authority. What? What in the name of... what is happening here? Is this image missing CA certificates? Yes. Can it hot reload the names? No, probably not. What a fun day today. Let's just try to run this container again. Okay, it automatically rebuilt and restarted the process. And this time also disabled the leader election. And now it's syncing successfully. Okay, I'm just gonna count this as a win, even though we had to ignore core DNS's demands for an initialized node. I'm really curious how we are doing it for our setup, our upstream setup. I don't think we are doing anything special there. And we also need to talk to the API, so I don't know how that would work. Anyway, let's commit our changes and then take a look again at the load balancer code. Git commit. Still has some issues with DNS on startup. Okay, nice. Nice. Let's get into coding then. 1.5 hours of setting up some weird pipelines. I hope it wasn't too boring. Coding. Should we test the functionality? Yes, let's test the current functionality, just to verify that everything works as we would expect it to work. Why is k8s so slow in the Goland terminal? CCM from scratch. So much quicker here. Okay. We want to verify that it set everything as we expected. So let's take a look at the nodes. We see a bunch of beta flags, but we're just going to take a look at the stable flags. We see that instance type is properly set. The region and the zone are also set. Then we have the the addresses. So we have the host name and the external IPs. Perfect. The provider ID is set, and I think that's all. Don't think we did anything else here. Yeah, okay. That's good to see. Let's quickly do the same for the other node. Ah, yeah, the taint is removed. Yeah, that's true. We have the addresses again. We have the labels, zone, region, instance type, and a provider ID. Also very nice. That's for the instance v2 controller interface, whatever. What about the service? Let's create our service load balancer. This is just a single pod running Nginx, and then we have a service of type load balancer that targets the pod that we have here and sets up a simple port 80 running to the Nginx. Let's apply that service load balancer, and then we should see a service in here. Okay. I just applied this against my home cluster, my private cluster. Let's quickly undeploy this and export the right kubeconfig and try that again. Usually I have like the Git snippet here. I also have it for the hcloud CLI and for Kubernetes on my work laptop, which shows the current contexts I'm using for all of them. But apparently I don't have that on my desktop machine, because I'm not using it for development much right now. And I usually only have a single Kubernetes cluster I'm working with. Okay, now back in our development cluster, we can see that we have the Nginx service here, and it has 2 external IPs. And we can see that it has a node port configured too. Now we can go into the Cloud CLI and list the load balancers that we have, and we see here that we have the Kubernetes default Nginx service. This is the cluster name, the namespace, and the name of the service. And we can see that it matches the IP and IPv6 we had earlier. We can also describe this service, and then we see that it has a single service in here, TCP listening on port 80, directing to port 31822, which is the node port that we saw earlier, and we can see that both servers are part of the target list. And now if we open that IP in our web browsers, I just pasted it into the chat for you to try, then you see that we have a welcome page. Nice. So this was automatically set up by the Cloud Controller Manager. Here we can see that it ensured the load balancer and then had some problem writing back the IP, because initially the load balancer doesn't have an IP that is only available later. Nice. Okay, let's try to fix this bug here first. That there is an error, sync load balancer failed. That's unnecessary. That's an unnecessary event, just because in the get load balancer status we are always returning the IPs, but we should make sure that they are even available first before we return them. So let's define it this way. If load balancer dot publicnet dot IPv4 dot IP dot is unspecified, if not unspecified. So only if we actually have an IP, we're gonna put it into the status, and we don't put an empty value in there. Ingress dot append assign, yeah. And the value for that would be the first one here. Yeah, and that would be a v1.loadBalancer ingress. Nice. And we can do the same for the IPv6. Usually I would expect them to be defined at the same moment, but it's always nice to do it this way. To make sure that even if it's not defined, then we also don't need to return it. For example, if you disable the IPv4 or IPv6, then only one of them could be available. Okay, waiting for it to deploy. And it tells us that it successfully ensured the load balancer. Let's quickly delete and reapply that. Because the IP is only unavailable in the first loop here. Okay, it still complains. If not, okay, might be a good time to set up the debugger here. I'm quickly gonna check my configuration for the debugger, but there might be a token in there, so I'm gonna try to hide that from you so you don't use my project. Yes, there is a token. And it's actually running this locally, which we don't want. So let's get rid of this and let's add a new, I can show you the screen again, in-game, yeah. Let's add a new run configuration, which is a go remote configuration. And let's see the scaffold debug docs, debugging with scaffold. If I remember correctly, they have a example config. They don't. That's fine. I think we can just take the port that it tells us here and use that. Okay, and it should automatically build the binary with the right flags if we run it in debug mode. And yeah, everything should be fine. So let's rename that to scaffold and then run the scaffold debug. Build a new image here with the right flags. And then we can put a breakpoint here, we already did, and start the debugger. And this will wait to connect, and this will open a connection and then stop the... No, it opens a connection, but it continues the execution. So the process starts as it should. Connection refused. Okay, took too long to actually become available. Let's just restart the debugger. And here we can see that there is an API server listening, and there is already our debugger. So let's see, we have the status, and then public net. Okay, so there are some IPs. So that wasn't a problem, but also we didn't expect it to be a problem because that only happens during one of the first reconciles. So let's get rid of it quickly again and then create it again. Okay, so here we are in sync and our load balancer still has the same IP. So let's continue the execution. Okay, so now we are creating a new load balancer, or rather we created a new load balancer. So let's see if not is unspecified. Why does it tell us that it is specified if it's a nil? But actually, if it's nil, we could also... How can it be nil? Okay, let's just check for an explicit nil here too. If not, and read.publicnet.ipv4.ip. Okay, so in addition to checking is unspecified, we also check for is nil, and then the check should work. So let's abort this and restart the process under test. When running with the debugger, it won't automatically reload. It will rather wait for you to restart. So if you make any changes to the code, the debugging session isn't aborted. Okay, yeah, if you have any questions, always feel free to just write in the chat and we can answer anything you dream of. Okay, yeah, now it worked again. So let's delete that. And we forgot to set up our debugger. Nice. Let's delete that and create a new one. This is from the delete. And this should be from the new one. Yes, they are a nil again. So let's jump over there. And yeah, now it's properly jumping over these statuses. Okay. We kind of have an issue now where it doesn't report the IP back immediately. It rather waits until the next reconciliation loop. Is there some way we could tell it to wait for the IP load balancer status? Okay, so here we create the load balancer, but we kind of don't wait for the result. So what we could do is say arrow.client.action.watch progress. We pass in a context and the action. And then we get back then we can just wait for the error channel to close. So we get the progress channel and the error channel, and we can wait to receive something from the error channel. And if the error isn't nil, we just log an error. And in this case, afterwards, the load balancer should have the full status available in later steps. Okay, let's restart the debugger. Or rather, let's restart the scaffold debug process here locally. Okay, let's recreate the load balancer once more. And also watch the service here. It's still pending. Okay, seems like we actually need to wait and then reload the load balancer to make sure that it's available, that the fields are available. So then let's do a load balancer.get by ID as in the context as well as the ID, which should be result.loadbalancer.id. And then we get back the load balancer and an error. Okay, sorry, got got distracted again. Let's delete, recreate, and then watch the services. It's pending. And there are the IPs. Nice. So this works now without any problems. Let's commit this. Git diff. Sounds good. Let's make a commit from this. Fix issues on first AV reconcile with IPs. Nice. Now we still have two things left that I want to do regarding the load balancer. And that is, we had some to-dos here. Clean up load balancer services that do not belong to any service ports. What we are currently doing is iterating through all the ports that we are expected to have according to Kubernetes and check if we have a matching equivalent in our Hetzner Cloud API. But we don't do the reverse, where we check all the stuff in Hetzner Cloud API and delete the ones that are not part of our spec. So let's do that one. So for okay, so it's called ports in Kubernetes and service in our API. So for the services of our load balancer, lb.services, so for service in range lb.services. This will iterate through all the services. We have to check if okay, we are going to iterate through all the ports in our service spec ports list. Range service spec ports. And if service.listen port equals int port, then we're just going to continue, because that means we have found a match. But if we don't, okay, so this continue will, oh yeah, it will only break this one, right? But we want to continue this one. Okay, now it will continue the outer loop. And otherwise, if we get to the end of this list and we haven't found a match, then we can clean up that service. Client.loadbalancer.remove service, nope, delete service, context, and we can probably just pass in the service here. Oh, we also need to pass in the load balancer port, load balancer and port. So load balancer, and the port would be service.listen port. Okay, put some error handling on this. Action response error. Oh, we get back an action. We could wait for that action, but we can also continue onwards here. Okay. That should be it. Let's run scaffold dev again here, so we automatically restart the process when possible. And then we can check whether that properly works as we would expect it to be. For that, let's create another service in our another port in our service. GLS, let's just call it GLS, but send the traffic still to the HTTP port. Let's describe our load balancer. We can see that it created another service here. So we have the service for listen port 80 and one for 443. And now if we remove this again, that was ugly, then we should hopefully see that it ensures the load balancer and that the port has been removed. And that is true. We can see that we only have a single listen port left. Nice. Very nice. Okay. One last thing that we need to do, and that is the same for the targets. Here too, we only add new server targets, but we never make sure to clean up targets that do not belong to any nodes that we still have in the cluster. So let's do the same thing here. Target loop, where we iterate through the targets, and that would match the nodes that we are being passed here. So we iterate through the nodes, and then we have a node. And then using the provider ID, we compare the node in Kubernetes and the server in Cloud. So we say if server.id server.id server.server.id wonderful equals the provider ID, then we continue. Otherwise, we will remove the server target. This accepts a load balancer and a server, so that would be server.server.server. Target.server.server. What is this returning? Action response and error. Error isn't defined here, so let's define it. And yeah, that should be it for this. Let's wait for it to rebuild. And then let's add and remove some servers. Could not build. Oh, yeah. Okay, so that's running. So let's go into our dev.env and just add another server. This will add one more server. Waiting for it to be available. Actually, we can open another terminal here and say, okay, get nodes, or watch the nodes. And here we see that the new server was added and initialized. Nice. Okay. Now we should already see that on the target list. So hcloud local answer describe. We should see a third target here. Here is CCM1, and it's currently marked as unhealthy. Okay, still unhealthy. Perhaps that's related to that it didn't initialize yet properly with the CNI and the network connectivity. It's now healthy and everything is fine. Okay, nice. Okay, so now let's remove it and check that it's being removed from the local answer targets. Apply once more. It will remove the node. Before we run that, let's put a watch on hcloud load balancer describe that name. So let's run this. And then we should at some point see the node being removed from the target. You can already see here that, yeah, okay, there it was removed. Nice. I'm not even sure if that needs to happen in because we will also probably remove servers that don't exist anymore. They are probably removed from the local answer targets eventually anyway. But in case you want to keep the server and just remove it from the Kubernetes cluster, that's important to clean it up. Okay, nice. Let's commit these. Feature proper cleanup for removed port node. It's a local answer feature. And let's push that. Very nice. Very nice. Okay. Is there anything left we still need to do? Again, I was very much quicker than expected to set all of this up. I said I wanted to write some tests for this. Do I actually want that? I think I'm too lazy today to write some tests for this example code. Is there anything we can clean up? Could probably wait for the progresses down here. I mean, we could take a look at the roots. The roots interface. List roots, create root, delete root. Sounds simple, doesn't it? Sounds simple. Okay, yeah. I mean, we got the time. Let's try to implement the routing setup for this. We need to make some changes to our development environment for that, because the routing only works if you have a network. So let's create an hcloud network. I don't know, let's call it cluster. Name is CCM from scratch. The IP range is equal to just the widest range possible. Do we need to put a network zone on this? No, I don't think we need anything else. But what we do need is the subnet, hcloud network subnet. And there we have one using a smaller subnet. It belongs to the network we just set up. The network zone, because we use the Falkenstein, the network zone is equal to EU central, and the type is of type well, it would be nice to have some inline help. Subnet, network subnet. Server, cloud, or vSwitch. We try to add cloud servers to it. Ha. Nope. Wrong docs. Docs. Start cloud. Networks. Network subnets. Add a subnet. Type of subnetwork. Well, that's not documented in here. Is it perhaps in the general network documentation? When a cloud service attached gets an IP address assigned from a subnet of type server. Connect cloud resources into your network. Was used to connect only cloud servers into your network. This type is deprecated and is replaced by type cloud. Okay. So let's use type cloud. And then we also need to assign the server to the network. So let's put a network block in here, and then we are going to use the subnet ID. Let's check out how we should do it. Server network. Okay, what we can do is we can make it using a new resource, server network, that will assign the server to the network after it's been started. But here, let's keep it simple and use the network block. For that, we need to use the depends on, because we need the subnet, but we assign it to the network. So we have a network ID equals hcloud network dot cluster dot ID. And then we have a depends on the subnet. Let's do the same for the workers. Perfect. Can we use this from in here, because we kind of specified the external IP, but doesn't seem like that's possible. Okay, let's apply this for the moment. We will need to modify Cilium also to work with a native routing mode, but we don't have that right now. Right now we are only assigning the network. So we create a new network and a new subnet, and then modify the existing servers will be part of the network. Perfect, that's what I was hoping for. Still working. Okay, they are part of the network. Nice. Okay, next we kind of need to tell our Cloud Controller Manager what network it needs to consider when doing all of this. So let's amend our existing secret and just add the network ID in here, which should be hcloudnetwork.cluster.id. And then we can pass that to our deployment here. So let's do another one, network, and that's just from the network key in the same secret. Perfect. Okay, 2 changes to the existing controllers we can already do. The first is that we can get the private node addresses and also return them. For that, let's first load our environment and save it. So we have the network ID, which is an int64, hopefully. So os.getEnv hcloud network, and then we parse that as a ID. So string conf parse int. Parse int accepts the string, the base, and the bit size. So base is 10, bit size is 64. And then what is the shortcode to Alt-Shift-Enter? Alt-Shift-Enter. Okay. Perfect. And then we can pass in the network ID here. And then when we create our other interfaces, we can make it available. So now in instance v2, we also need the network ID to be available. So let's pass it in there. And then in get node addresses, we can also pass in the network ID, i.network ID. And then we can iterate through the networks of our server. So private net in range server dot private net, and if private net dot network dot ID is not equal to network ID, then we can just continue. And otherwise we can check if basically we can do the same as we did here. So if the private net.ip, if it's not unspecified, then we can append that to the list. But this is not a type node external IP, but instead node internal IP. Nice. Should we see if that already works? We probably should. I could not find key network in secret. Let's see if we didn't properly apply that change. And we actually didn't. Okay. Also, we are running into a bug with Terraform 1.4 and above, which is already reported but requires some extensive fixes to actually fix. So let's say alias IPs is equal to an empty list. Okay, so the bug is if we don't specify the empty list here, and this is a block of arbitrary length, we don't properly set the default, so Terraform thinks that it needs to recreate this every time. And this will actually reattach the server. So remove it from the network and then reattach, but that's unnecessary. When we specify the empty list explicitly here, then it will properly fix this. Detect that it didn't change. It's a deliberate bug that Terraform included in 1.4 because we were using an older SDK where the alternative only went general available last year. Okay, so the secret is updated. Oops. And our deployment should go through now. And it actually did. Nice. So let's check out our servers if they already have the updated private endpoints. Let's describe our node. And there we can see the internal IP. Perfect, that's what we were hoping for. Check the other node too, and it also has an internal IP. Nice. That was quick. Let's commit the changes that we have so far, and then do the same for the load balancer. Okay, one downside of what we just did is that the code is now dependent on a network, which some users might not want to use, but to keep it simple, again, we're just focusing on a single use case here. Okay. Next, let's think about the load balancer. And a load balancer can be, where is it? A load balancer can be a part of a network. You can actually pass it the network here. Yeah, so let's do that. Network ID in 64 and in cloud we need to pass it the network ID. Yeah, when we create the load balancer, we can set that it is part of the network. Let's just create a new network here. Okay, and then we can also tell it to use the private IP to talk to the targets. Target, update load balancer target. So here in add server target, we have the use private IP bool, which we can use to tell it to use that. So use private IP is pointer group. We have an utility function here for a pointer because you can't take pointers of like heap stack allocated variables. So we need to make sure that it is being heap allocated. We do that by passing it to a function, and then that function can take a pointer of it. I hope that explanation is correct. I am not that deep into the Go internals, but that's the effect of what you as the user need to care about. Okay. Yeah, let's see if that's running. Deployment stabilized. Okay. Bit curious that we don't see any logs, but let's just assume the best and that it successfully deployed. Let's delete the service once more because we didn't handle going from no network to a network. If you do it, you would actually need to like handle all these changing variables everywhere, but we don't wanna. We got a load balancer, so let's check out the configuration for this. This is CCM from scratch. We see our two nodes, and under load balancer, we can see that it has two targets, is part of our private network, and both targets are unhealthy. That might still be the first iteration though. We're gonna see later. We also see that it has a private IP, and we don't see whether it uses the private IP or not. Might be that this is just not available in the frontend, or maybe once this column is set, it uses the private IP. There's also some Z issues, Z index issues. Okay. Let's actually try to hit that endpoint. Connection was reset. Okay. What did we do wrong? did we do wrong? Let's check out the configuration in Kubernetes. Let's not use k8s from here, let's use it from here. So we have the type load balancer, and it's registered as expected. The node port is 30,681. Matches. Also matches the internal IPs of the nodes. Oh, okay. Yeah, seems like Kubernetes has some issues because the setup certificate is only valid for the public IPs, but not the private IPs. So we might need to recreate our Kubernetes cluster, or at least do something like that. Okay, how do we do that on the script that I know that is working? Okay, so we set the external IP as well as the private IP. So let's do the same here. So node IP is equal to self dot network that can't work. Let's take a look at the state. Terraform state. Oh. Doesn't have some kind of console. Terraform console. What is the value of hcloud server.cp.network? Yeah, it has a 2 set. So if we do 0, yeah. Okay, can we do a to list on the network, and then we take the 0th element? Does it work like this? To list. Yes. Yes, perfect. Okay. So let's do this for both of our nodes. And then destroy and recreate everything. So Terraform destroy. Yes. This is going to take a moment, and then we can recreate that. Still destroying. Oh, yeah. It probably won't destroy on its own because the load balancer is still there. Because that was created in the cluster and not in Terraform, it wasn't properly cleaned up. But yeah, now it destroyed. So let's run the apply again. And after a minute or two, that should be done. First node is initialized. Waiting on the second. This is another thing that could be optimized by using the null resources, because then the second server could already start up while the first one is still doing the Kubernetes initialization. And then you would just have the null resource that does k8s up at a later time. But I think it's still reasonably fast here. Especially if you only need to set this up once a day. Signed by unknown authority. Okay. Let's try to talk to the API ourselves. That works. Oh, probably because it read the kubeconfig while we were still starting. Can I give a provider defense on? Does this work? Nah. Okay. Unfortunate. I guess if you do it in different modules, it would still work. But right now we can just execute it twice and get to the expected result. Okay. Now the secret is created. We can connect to the cluster. So let's run scaffold dev. Once again, core DNS isn't properly starting. And we can't get DNS resolution in our thing. So let's update the core DNS deployment and add the taint. Yeah, that's certainly something that should be fixed if we plan to work on this longer term, but we don't right now. Core DNS is running. Let's restart our pod here to make sure that he gets a proper DNS refresh. And there it initialized the nodes. So now that taint has been removed. No taint in here anymore. And also we got the internal IP set up properly. Okay, let's create the service. Service was created, ensuring load balancer, ensured load balancer. So it has 2 targets and it's waiting for the status, and the status is there and it's healthy. So if we go to that IP, we should see the traffic. But we don't. Because now they are unhealthy. What is the problem here? Let's try to SSH to one of these nodes. Can we, on our own node, access the port? Why can't I copy that port? This is really annoying. If anyone from the UX team is watching, please just make stuff copy pastable more. 31137. 31137. No, we can't. Okay. Can we connect to the port direct to the container directly? Wait. Why is this IP in the pod CIDR? What pod CIDR do we have configured? Devenv cluster CIDR. That's not part of the cluster CIDR. What? The IP for the pod is wrong. Okay, let's set one more flag on Cilium values, and that is that it should use the Kubernetes IP address management. IPAM mode Kubernetes. Yeah. Values. What is values? In raw YAML. List string. What? Okay, so we can just use set. Set name is IP mode, and the value is Kubernetes. Let's try to apply that. Is that the right one? Yes, IP mode needs to be Kubernetes. Yes, please. Okay. Still gets a bad IP. I mean, we could roll out the cluster again, but I kind of don't want to do that. Let's try to restart everything. Okay, so there we have the first pod that has the right IP. Let's try to restart this once more. They are probably running in host network, right? Host network, yeah. Metric server, let's restart that one. Now it's also running in the right IP space. And then we want to recreate our Nginx pod, because that doesn't use a deployment or anything. That wasn't automatically restarted. And now it's also in the right IP space. So now if we are on that node, cloud server SSH, and we do a curl 31137. Was that the right port? 31137, yes. We get back a successful response from Nginx. Aha, nice. So now we only need to wait for the health check here, which happens every 15 seconds, and we should get back a successful response. Yeah, first one is healthy, and second one is healthy. Nice. Very, very nice. Okay. There's a lot of pain in configuring a Kubernetes cluster. Always remember that. Okay, nice. Well, seems like it's still not working. Ah, okay, it is working. Just not this one. This one now too. Okay, nice. Nice. I'm running out of time. I got a doctor's appointment soonish, so we can't do the actual implementation. One thing that I want to check is can we see whether it's talking to the private IP or the public IP? So let's describe our load balancer. Use private IP, yes. Use private IP, yes. Okay. Let's test the front, and then how does it look like if we don't use the private IP to talk to one of them? Let's remove the control from this one. And let's add a new target. Let's use the public IP. Okay, so it's not showing up as, doesn't have a private IP here. I think that could have some nicer UX. Might give some feedback to the team later. Okay, let's remove it. And yeah, we can actually just start the controller again to add it back. And then let's tear down the dev.env and review what we've done today. Say, going out message. Ensure load balancer. There it is. Nice. Okay. First, let's start by. Oh, no, we still need that deployment, and then we want to delete the service, just so we don't have to clean it up manually. It deleted it, and then we can run Terraform destroy. Yes, please. Okay, to review what we have done today. We started by setting up our development environment. We're using Terraform and k8s up for this. We defined a TLS private key, uploaded that public key to the Hetzner Cloud API, so we can use it to create and manage servers. We created a network and a subnet. We create a server for the control plane, for the server in k8s speak, that we configured using k8s up, similar to what we did last time, but this time in Terraform and not by manually executing k8s up. Then we have a number of other servers here, an arbitrary number of other servers, which are part of the same network and subnet, but which are just joined to the existing cluster. We also used the Helm and Kubernetes providers to install Cilium for our networking interface and to configure a secret with a token for the Hetzner Cloud API, as well as the ID of the network. We did some further fixes in the load balancer. Previously, we did not properly clean up services as well as targets of our load balancer. So in Kubernetes speak, the pods and the nodes that are part of the service, we didn't clean them up. We just created them, and now we also clean them up. We fixed a bug around the IP addresses not being available, which we fixed by watching and then reloading the load balancer to get the actual IPs to write back into the status of the load balancer. And yeah, lastly, we added some private networking functionality where we add the network ID to the node status as an internal IP, as well as attach the load balancer to the network and make sure that the load balancer is talking to our servers using the private IP. Where does that happen? It's here at target use private IP true. And yeah, that's it. That's what we did today. Yeah, I had a lot of fun building the dev environment out, and also these loops weren't as complicated as I was thinking last time. Actually, they're like even simpler than the other loop because we don't need to care about updates. Yeah, so let's make a last commit for the day and then bring the stream to an end here. Okay, feature load balancer, use private IPs to talk to targets. Git push, and yeah. Thanks a lot for coming by the stream today. I hope you learned something. I definitely did. And see you next week. I guess we are gonna implement the routes interface next week, and I don't know, start talking about the CSI driver. I'm gonna make a better plan before next week, and then we're gonna do whatever my plan says. Thank you very much, and have a nice day. Goodbye.